stability is important because of this. So think of when we are solving a differential equation, right? Think of it's a little bit. Let's use a different notation. Let's denote the numerical solution as u hat, right? So all of these numerical solutions we have so far, we used u to denote it. But now, because we are looking at the difference between numerical and analytical solution, let's denote the numerical solution as u hat of I, right? Because we are solving for the solution at grid points. And we know because we are making errors, we are not getting the exact solution, okay? Denote the exact solution as u of I. So imagine we are solving an equation with certain boundary conditions in which we can actually analytically derive the solution, and then we take the values of the analytical solution at the grid points I. Okay, so what's the difference between ui and ui hat? So define e of I being ui hat minus ui. All right. Okay, so the question is, what is dei dt? How does the error grow? So imagine our initial condition is actually exact, right? Our boundary condition is exact. Our initial condition is exact. So ei would be 0 at t equal to 0. So ei is, there is no error in the beginning. How does the error come from? It has to evolve in time, right? Okay, so dei dt is equal to that, and is equal to dui hat dt minus dui dt, right? Okay, so what is dui hat dt? The matrix one, exactly. So it's ui plus 1 hat minus ui, plus ui minus 1 hat minus ui hat, right? So that's basically our numerical scheme. Okay, minus, but what is dui dt? How does the analytical solution evolve as a function of time? What does it satisfy?
Kappa times AU.
Oh yeah, we have a kappa times, sorry. Yeah, kappa times what?
Kappa times A times B plus B.
That's the numerical solution. That's how the numerical solution would evolve. How does the analytical solution evolve? What equation does the analytical equation satisfy? Yes, the differential equation, right? Okay, good. So, this is a little bit different from the error analysis we did before. The error analysis we did before, using Taylor series analysis, right? If you remember, we are looking at the difference between the finite difference operator and the analytical derivative operating on the same u, which is different from what we get here. We are looking at the finite difference operator operating on u hat and the analytical derivative operating on u. So how do we resolve that difference? Subtract and add. That's a great idea. So let's do that. So let's think of, okay, so what we should subtract and add. Let's subtract and add this. Let's subtract and add the finite difference operator operated on the analytical solution. Okay. We do this minus ui plus 1 analytic. We don't have hat here. Okay, we're going to add the same thing. All right, done. Good. So the second part is exactly what we analyzed before. We know that is proportional to O, something like delta x over 12, right? That is delta x squared over 12 times the fourth derivative of u and plus O delta x cubed. So that's what we analyzed. We know if we have an accurate approximation, if we have delta x to be small, this is automatically small. Stable or not, it doesn't care. But the first term, right? The first term is the finite difference operator operated on the numerical solution minus the same operator operated on the analytical solution. Or if you use the definition of EI, that is the finite difference operator operated on E. Right? Okay, so let me write it down. DEI dt is equal to the summation of two parts. One part, this part, is determined by the accuracy of the scheme. If somehow I have a scheme with zero error, so let's say this is 0, then my EI is going to stay 0 no matter what, right? I don't care about stability. But in the real world, there is no scheme with 0 error. So this can be made very small, but it can never be 0. Once this is not 0, it'll create a non-zero EI. And then the rest of the time, if EI is going to be big or not, depend on this, right? If this term is going to be exponentially decayed, if this term doesn't accumulate, then the magnitude of EI is going to be primarily determined by this term. But if this term is exponentially growing, okay, then my EI is going to be exponentially growing, even if I have a small error, right? And then how big EI is may not be actually determined that much by this term, but by how fast is the exponential growth. All right. So that is what we see. I mean, what we see, the instability is actually not the instability of this equation, but the instability of the equation after we also discretize the time derivative term, right? So we see an instability over there. And we saw a case where actually a smaller delta t actually led to a bigger growth. Not because the smaller delta t has a bigger error, the smaller delta t naturally has a smaller error. But that smaller delta t actually has a higher rate of growth, right, from the self-feedback term. Right, this is a self-feedback term. Once you have a EI, you may get a bigger EI at the next time step. Then you may get an even bigger EI at the next time step. And it's kind of a positive feedback. So in that case, we just saw that delta t equal to 0.01 have a bigger error because this term has an even faster positive feedback. All right, does it make sense? So we'll analyze stability more, like in the next lecture. Like basically look at when you have a numerical scheme, how do you analyze if it's stable or not in the next lecture. But this lecture, we are just introducing the idea that doing error analysis to the differential operator is not enough. You also need to know if your numerical scheme is stable or not. Okay, and that is basically you need to look at. If you think of this term, if you write this term as a matrix, right? You need to know, does my matrix, I mean, what is the behavior? What is the spectral property of the matrix? Does my matrix has eigenvalues on the positive side of the complex plane, or everything is on the negative side of the complex plane? That's very important in the spatial discretization. When you talk about temporal discretization, then some other region in the complex plane is what you should be considering.